Back to the Engine Performance Expo. Joe Castello, Lake Speed, and we are joined for Hidden Horsepower Live by Mr. Billy Godbold. Billy, welcome. How are you?
Doing great this morning. How's everything going?
I am excited. But I'm especially excited about this because we're going to delve into your career a little bit, talk a little bit about some of the projects. I know you two know each other very, very well.
Yep.
Nice to meet you.
Billy Godbold, Lake Speed. Yeah, I've seen you on Hidden Horsepower.
Oh, yeah.
I've seen him everywhere. Are you kidding me? Not just in horsepower, but in many places. Your vast knowledge, we joke about it a little bit, right? Lake says, like, this guy's launching rockets. Mm-hmm. But in reality, that's kind of something you studied.
Yeah, my background's in physics. I went more for the real small stuff. I was in nuclear physics, so we accelerated really small things really fast. But my background is, I grew up on a farm in rural Mississippi, so I was around motorized equipment my whole life. It's kind of neat, the combination of understanding the macroscopic, the big things and how they work together, and trying to understand the microscopic, how things work down at the atomic level, subatomic level.
Well, and we've been talking about car parts and making horsepower and everything, but when I get an opportunity like this to speak with someone that is clearly got a range of knowledge and experience far better than I could ever understand, like, what's the secret of the universe, Billy? Like, what's going on out there? Give us the real answer. Wormholes, are they real? Are they possible? Can we fold
String
time?
theory, come on,
what's
let's
coming?
go.
Yeah, have fun with that. No, it's funny because, when you're in physics, you go one of two roads when you go in grad school. There's one group of people that go into experimental physics. The other group goes into theoretical physics. I went toward experimental. My idea was, when you're experimental physics, you're waiting for somebody to talk about wormholes, and then they go, okay, well, what would all this look like in the universe? And then you spend your career trying to prove the theoretician, the guy who came up with the theory. Your job is to prove him wrong. You prove him wrong, he gets upset, he jumps out of a window, hopefully it's a low story. And it's kind of fun, so that in my side of things, I love listening to the theoretical side of physics, but I enjoyed the practical, the experimental side even more, when we talk about that in valve train, you think, okay, well, Billy, how do you use that in something like valve train or something in engine parts? Whenever you see a failure of a part, you look and that part's like broken. But that part never just fails all at once. Every failed part starts with a very microscopic failure. So we start looking under a microscope. We start taking sections. We start looking at scanning electron microscopes. We look at the chemistry of it. We look at the surface finish. We look at everything to try to find out where at this very microscopic level. When you talked about steels, it's down at the lattice. It's down at the atomic level.
Right.
Somewhere at the very atomic level, the applied forces were greater than the strength were at that very small level. Once you do that, that part of the steel initiates a failure. That failure propagates, and you may wind up pulling a dyno, and all of a sudden there's a connecting rod hanging out on the side, and oil's on fire and everything, your fire suppression's going, and everybody's screaming and hollering. But that didn't happen. The whole connecting rod didn't fail.
No.
There was a atomic level microscopic failure that propagated. And so that's one of the neat things when you have a physics background, how you bring it into something practical, is understanding, let me figure out where it failed. And then once I figure out where it failed, everything fails because the applied forces were greater than the strength of the material.
Yep.
So all I have to do once I figure out where it failed is, was the material strength lower than I thought it would be there at that microscopic level, or were the applied forces greater than I thought they would be at that tiny spot? And then you just address that. So it takes something that's as complex as this major fire in your dyno room and breaks it down to what happened there.
Right. At this microscopic level between this atom and that atom.
Right. And so you go, how does a nuclear physicist wind up in race at 25 years in racing? It comes down to something as simple as that, trying to take a big problem and break it down to something very, very simple.
And have solved a lot of problems along the way because of it.
No, we've had a tremendous time with that. It's been very, very neat.
It's been a lot of fun. And a practical example of what you were just talking about, relate the story about what surface finish, surface texture, actually.
Yeah.
How that impacts the choice of steel and that applied load and what causes the failure.
No, we talked about this one time. In my position, I get to interact with some very, very cool people. Lake and I actually wind up dealing with a lot of the same cool people from different ways. It's because it's a friend of mine who's a friend of his, and he's over a major, commercial diesel setup. And if you look at over-road trucks, they have to have a 1,000,000-mile warranty.
Right.
You do the math real quick. It's going 1,800 RPM at 60 miles per hour. That's roughly for a million miles. That's roughly every valve spring opens and closes. Every lifter on a cam goes around roughly 1 billion times.
That's a lot.
That is a lot. And so I've been doing all kinds of material research. I love material research. If I was ever going to be something other than a physicist, I think I'd be. I think I'd go into material sciences. I love metallurgy. So I'm talking to him about these different metals. We're working with carpenter steel. We're coming up with different steels and everything like that. And I'm talking about all the different stuff. And I'm like, well, we had this that was 240 KSI. Then we had this that's 280. We had this that's 290.
So
had this that's 300.
KSI is tensile strength.
It's tensile strength. It's thousands of pounds per square inch. Actually, steel. People think steel breaks in compression. It actually always breaks in tension.
Elongation.
When a valve spring breaks, as you're twisting it like a torsion bar. You create a pull somewhere in it.
That's the dislocation at that atomic level that propagates to the part failing.
Right, exactly. When a cam lobe fails, you'll often see it'll fail at the edge. It's because where the lifter's pushing, it's pushing down, and it pulls apart right at the edge where it's loaded. So it's actually pulling apart, not compressing apart. Every failure is usually a tensile failure. So I was talking to him about all these metallurgy. I'm like, well, what materials have you guys been using to make this? And he's like, well, we've been able to make everything twice as good. And I'm like, what?
What unobtainium metal do you have?
Exactly. Well, you know that you're around 250 KSI, and the best stuff in the world's around 300, 350.
The math doesn't work.
You can't get to 500.
Right.
There's no 500 out there. And where he started to talk to me is it made the whole change. It changed us to, instead of looking at improving our materials, it changed us back to looking at our surface engineering.
Right.
Because he's like, Billy, look at my bearing areas. I used to be 30%. Now I'm 60% bearing area. It's RMR, it's material ratio. There's a lot of different words to describe bearing area, but it's just about at a certain depth under of every surface finish looks like a mountain range if you look close enough.
Nothing smooth is actually smooth. It's always rough, peaks and valleys, kind of like the terrain around here.
Right, exactly. You go to my side of the state, it looks smooth. If you get under a microscope, it's actually still rough. The same thing. If you look at these over here, we got mountains over here. But if you look close enough, every surface is mountainous. And what he was doing was finding ways to make the mountains more like plateaus.
Right.
Less like peaky, not the Grand Tetons, more like the
Appalachians.
or the Cumberland Plateau. In between,
exactly.
So very flat top, and he was able to double the bearing area that his lifters were riding on, and it really changed. This probably was 7, 8, 10 years ago.
Yep.
It changed the way we looked at camshafts. We went from going total on material technology, and we shifted to surface engineering. We never gave up what we learned on the material side.
Right. You just combined it and said, hey, listen,
right.
It's way easier to do push-ups on your palms than it is your fingertips.
Yeah. Well, it's the whole thing. It's like you when you want to look at things from a scientific point of view, you try to look at how much is there that I can improve. When you're at 30% bearing area and you can go to 90% bearing area, you can make it 3 times better.
Which is,
if you're at 250 KSI and you can only get to 300 KSI, you're not going to double it. You're not going to make something a whole lot better. So where do you want to put your time? Where do you want to put your resources? Where do you want to put and focus your money? You focus it on where your best return on investment is. You want something that can really pay you back, and we've had tremendous luck with it.
That's when it's nice to know a guy like Mark Barberg.
Yeah, well, absolutely. The conversations we've had, the way he's educated me on surface engineering, just a tremendous guy.
And his software is so wonderful because it takes the information that a profilometer can gather for you, and it just makes it kind of come alive where you can visibly see it. 'Cause it's great to have the numbers. Like, for us, for piston ring and cylinder finish stuff, we're looking at, RPK, RVK, and RK. You're looking at MR1, MR2, and things like that. The number is a great thing to have. I mean, but when you can see it visually, you can see those mountain ranges and see that it looks like the Grand Tetons, or if it looks like the Cumberland Plateau. That visual part really helps.
Right, and he does the best job. From an engineering level, you and I can look at some of those numbers, and we've already got the graphs in our mind of what that number looks like.
Yep.
But when you bring somebody into your quality program who hasn't seen this their whole life, hadn't been around it, instead of taking a year or two to get them up to speed, what the software we bought from Digital Metrology, it would make graphs, it would make it easy so anybody look at it and go, okay, if it goes outside these bounds, it's bad.
Right.
And it really makes it where somebody doesn't have to spend 5-10 years of education to try to get up to speed with what we're trying to do.
Exactly.
And not only that, helps helps them understand why we're doing it.
Oh yeah, it's the why. If you can understand the why, then everything else begins to make sense.
That's one of the things that we've done for years at Comp, trying to work. We have the same guy who's the first guy we had grinding cams is still there today.
Really?
Yes.
Man,
Kenny Arundel.
Kenny.
I'm employee number like 4,000 something. I think we're like 50,000 somewhere. He's employee like 00001.
Kenny Arundel. He's a legend, by the way, in the camshaft industry. People know.
Oh, like literally, like if you watched any NASCAR race in the 80s and 90s, and your driver won that race, the chances that Kenny ground that camshaft
are like nearly 100%.
Right, it's way over 95%. It's like, but I like Mark Martin. Okay. I was rusty. Okay, DW. Yeah, Dale.
Kel Yarborough going 200 at Daytona for qualifying.
Still had the camshaft.
Yeah, there you go.
There's all kinds of stuff from that. So being around people have that, but I guess where I was coming from is, we do this stuff to try to, one of the things, the reason we try to do the graphic side of it, that we're trying to explain it, is when the guy's grinding the cam and the guy's checking in a QC, it's not enough for me and you to know what's going on, or me, you, and Mark to know what's going on.
Right.
But trying to show it throughout, so our sales guys know what we're doing, our guys at the grinder know what we're doing, the guys in quality know what we're doing, and we know why we're doing it.
Right.
And it really helps everybody get on the same page and know it's important.
Right.
So it's neat, and we see it throughout one of the neat things about being in performance and racing is you don't have a lot of people who are accidentally there. In some industries you go and the guy that's doing packaging, well, he just needed a job to do packaging.
Right.
The guy who's working in QC, well, he just needed a job. Most of the people who come in our door and who've been around for years, they love what we're doing. So it's so easy to get them excited about it. Like, here's what we're doing, here's why we're doing it, here's why it matters.
Yep.
They get it, the light bulb's on, and then they're passionate about it. Then you're walking through the place and they grab you and say, hey, look at this, what do you think about this? Could we do this? Could we make it better?
Right.
And I mean, like one of the guys who runs one of the big finishing machines, he comes up to me all the time and he has great ideas. So we have it, there's not just a one person pushing, there's a whole team effort trying to make things better every day.
That's cool.
Yeah, Jackson's amazing. If you ever get in touch with him, man, he looks at every camshaft that comes out, he's looking at it and he's like, hey, what do you think about this? It's awesome.
Talk about, just for a minute, I know, Joe, I tried not to steal this and just ran off the rails, but we did anyway.
I have the best seat in the house. You guys think you got something good going on. I do too. We got a question or two.
Yeah.
Keep them coming, but what were you going to say?
Yeah.
Talk for a minute about the MSC process and what that is and why it's so important, because it does kind of relate to what we were talking about here.
It's all about, if we started with the whole thing that we talked about, microscopic going to macroscopic, the MSE is something that goes from the very beginning. A lot of people think that when we did our MSEs, that's just a polishing. Right. It's a polished camshaft.
Well, because it looks polished, right? It goes from normal metal finish to something that looks more like this, just shiny and looks
it's a
good.
shiny camshaft, and
Right.
people go, okay. I mean, what's funny, we put the MSE in, and I got these calls. I got like 4 the first week. They're like, "Hey, Billy, I got one of your trade show camshafts." You know. So in the trade show, what we do is often we go and take a diamond belt, go over the lobes, make
Right.
it shiny. So it took a great picture, right? People would go, "Oh, I got a polished trade show cam." But really, what we were doing is very much like what we were talking about from what Mark was doing. The MSC started with the grinding wheel we used. So we worked with the grinding wheel manufacturers, worked with the cam grinders to try to get even the dressing wheel. How did we dress the contour into the wheel? What was the finish of the lobe? And then grinding that finish, and then afterwards you go in and you polish the tips up.
Right.
But it's very much like if somebody was going to buy, I'm not a big baseball guy, but if somebody was going to go out here and say, hey, we need to build a MLB baseball field out here in East Tennessee,
Okay.
you wouldn't start with the finishing mower. Out here,
No.
you'd start with dynamite.
Right.
You know, and you have to
And
blow
bulldozers.
blow this rock out of here.
Right.
Then you bring bulldozers in. Then you bring graders in. Then you bring dirt in, and you do all this. Then somebody plant the grass. Now, before it got on TV and they showed something, somebody would be out there with a finishing mower making that beautiful grass to look just great. But the mowing the grass doesn't make the baseball field. It's the end on the baseball field.
Right.
Very much the MSE, the polishing isn't the MSE. The polishing is the last step in the MSE.
Right. Of creating that surface
Right.
finish, that texture that can hold oil, support the load, and
Right.
basically but those two
But
things.
without the right grinding, just like in a honing where you have to have a certain, first rock and second rock before you put that last rock in it, the grinding wheel is just as important
Right.
for creating the mountain range that you're going to mow. We've got to create the grass before we mow the grass.
Right.
And if you don't have a nice field of grass, you can't mow it right.
It's a process.
If you polish an inferior camshaft with our MSC process, you go through the last step. If you put a bad cam in there, it comes out looking double bad. It doesn't hide imperfections. It'll actually bring them up.
That's kind of cool.
Yeah, it doesn't make a bad part look good.
Doesn't hide anything.
No, it's like these lights under here. I can see every speck in my glasses under light. People talk about like car finishes. I'm not a car show guy, but like they'll tell you, okay, that's a 12-foot finish, and you're like, 12-foot finish? Yeah, if you stand 12 feet from it, it looks pretty
okay,
good.
yeah.
Like on my car, mine's about 4 miles. From
Right,
4
right,
miles away, my car looks really, really good. The same thing when you start doing a good super finish routine, a good micro polish. We use a high energy centrifugal micro polish system with some very, very some really neat media and burnishing compounds we use.
Right.
When you run it through there, if we took our camshafts that we used to grind before MSC and ran it through there, you would see all kinds of waviness and some chatter and dress marks and everything like that. To do this finish, you had to have a better deal. Very much going back to the baseball diamond, you can't go out here in any cow pasture, just plant grass, run a finishing mower over it, and have a good-looking baseball diamond.
Yeah, and like the idea of the tape polisher. Yeah, it'll make it pretty, but it's not applying that load evenly, so it could create this texture, this waviness that takes away load-bearing area.
Right. You can take a tape machine, and if you set it up wrong because it's got a conforming backing, you can make something bad, something that was good, bad, and make it look really good. Because we're using a centrifugal kinetic energy system, we're taking off material evenly all the way across. So if there's any waviness, it's not gonna make it any less wavy, but it will absolutely show it because you'll see how the light bounces off of it.
That's cool.
Yeah.
All right, question from Tim.
Yeah.
Ask Billy if now's a good time. As Tim
What?
says, thank you, Tim, for your courtesy
Yeah.
out there. Ask Billy to expand on compression ratio and intake valve closing. If not now, maybe later today.
No, I mean it's a real interesting one because you hear people talk about you'll see things about cranking compression, dynamic compression, everything like that. And what they're trying to do is figure out for a different fuel how can I run pump gas at like 11 to 1? And so one of the tricks is to lay the intake closing. What people don't realize is what you're really doing there is you have the highest cylinder pressure at peak torque.
Right.
At peak torque, that cylinder has filled the absolute most. If you create too much pressure, the gas can become volatile and it can pre-ignite. And that creates a really weird explosion, and then you create a spark over here and the two flame fronts hit and you knock rod bearings out and everybody gets upset. There's wailing and gnashing. All those microscopic failures, you're going to find lots of them.
They're going to come.
They're going to come. So what people have done over the years is they would know if I move that intake closing point later and later, I will move that peak torque to a higher RPM and lower. Normally, if you've ever heard a car rattle, often you'll hear it like on a street car, you'll hear it going uphill at like 2/3 throttle in a high gear. You've loaded the motor, it's filling really well, it's closing the intake valve, it's making all this torque here. But the only way to reduce the cylinder pressure at 2,500 RPM is to reduce the only reason to reduce the knock at 2,500 RPM is to reduce the cylinder pressure at 2,500 RPM, which also reduces the torque at 2,500 RPM. So it's not really a good idea. You would rather set up your compression ratio around the fuels you're using and not try to crutch it with a late intake closing unless you have to. Now, if you've built a 10.5 to 1 motor and you've done everything right, and dadgummit, this thing rattles and it's driving you crazy, absolutely, if you move that intake closing back 5, 10, 15, 20 degrees, every time you bring it back, it's going to reduce the torque there at low RPM, and you can make it better, but it's sort of not the right way to do it because you've reduced performance, you've reduced the throttle response, you've reduced torque in that low RPM. So when you do try to give it full throttle, it's going to be worse.
Got a question.
Yeah.
So based on that comment, do you think just changing intake valve lash, if you were really close to knock, you could actually move yourself?
Oh, absolutely you will. You can advance retard the cam. If you advance it, it's going to make it worse because it...
So just lash. Like
Yeah,
just
absolutely.
lash alone, right?
Yeah.
I give it a little less lash. Maybe I start off and I'm going to be a little loose just because I don't want to be it too tight and hang the valve up or something like that, right? And, everything's tuned. I tune it up good. And then I go, I'm going to tighten it up a little bit now because now it's kind of rolled in. And all of a sudden now...
Yeah, absolutely.
Rod bearings hanging out.
Now, the thing is that
because you're making the cam bigger or smaller
Each
that
time
way.
you change the lash about 4 thousandths, you're only moving that point about 1 degree.
Okay.
You're moving
So
the
4 thousandths about 1 degree.
Well, it's about 2 degrees, but it's one on each side. Yeah.
Okay,
so
got it, yeah.
4 thousandths is about 2 degrees, so it's about 1 on each side. You're going to have you probably, if you're hearing audible knock, and you change the lash 4 thousandths or 8 thousandths, you're probably still got a knock. You may not hear it quite as much.
Exactly, yeah.
All right, here's another question from someone out there. I need 50 more horsepower for this year. Any tips? Asks John Causey.
Hello, John.
Hey, John. That they really frown on nitrous on most of his classes. The thing is that John's way up on most everybody. So, when you look at engines and you're trying to make a power goal, the first thing you have to look is see how much airflow you have. And your airflow is going to dictate, the only thing you have to make power is fuel, and it has to be mixed with the right amount of air. So your airflow, and this is where John's just an absolute maestro, is getting a head that flows air dynamically. Not flows air on a flow bench, but flows air dynamically. Once you can get something that flows air, then my job on the camshaft side is usually I'll tune overlap around what room the piston guy will give me. You tune intake closing for the RPM you're going to run at.
Right.
You tune exhaust opening to limit the amount of pumping losses you have for getting the exhaust out, yet giving the longest power stroke you possibly have. So, people talk about duration and lift and lobe separations. Really, I'm looking at 3 regions. Okay, I've got this overlap region, I've got the intake closing, I've got this exhaust opening. And then it's about how
And your overlap's all about, you said this.
Right, the overlap is probably dictated by this guy right here, because the space-time continuum, back to physics.
Yes.
When you put a valve and a piston at the same spot, at the same crank angle, boy, you get some interesting microscopic interactions.
As I've said before, piston-assisted valve return is an imperfect science so far.
Right. You really don't want to, if your valve spring doesn't close your exhaust valve, your piston will. Yep. Not a good thing. But no, we're all trying to get this area and everything. So really, as valve train technology goes, as port technology goes, you think, 50 horsepower, that John's asking for something ridiculous. I wouldn't be a bit surprised if his mountain motors and some of the pulling motors he has, they really could be 50 horsepower better next year.
Yeah. With just some small changes.
See that, John?
Yeah, we got it.
We solved your problem.
Yeah, do a better job porting the heads.
Yeah.
Then I'll get you a camshaft for it. Yeah.
I'm not jumping in on it, John. I think you're doing great, just so you know. Interesting angles out there, like on Hidden Horsepower, and we encourage you all to subscribe, Apple Podcasts, Spotify, just type it in, wherever you get your podcasts. At the end of each episode, we ask about advice for the next generation. But I don't know if the next generation is out there watching the Engine Performance Expo, but just general advice to engine builders out there on how to go through their process, right, and maximize their situation. Knowing what you know, what's a good starting point for them? Like just a way to think. We've talked about this a lot in the past. Like, how to think about the project macro.
Yeah, and I mean, that's kind of what I was alluding to. And you'll hear it, I probably heard it in the past 2 days 50 times. Make one change at a time, then optimize around the change.
Right.
Notice when I was talking about how we do camshafts, I didn't say, hey, let's throw a new lobe in there. I said, let's look at each of these 4 valve events. Or maybe we want to keep the same lobe in there, keep the same 4 valve events, but try a lobe. You see somebody go and change the intake duration, exhaust duration, the lobe separation, everything like that, and they try this new trick cam all at once, or this new trick piston all at once, and they take or this new valve spring, or this new push rod, and they try a lot of changes at once, and they just get totally lost. But even if you just make one change, say you try a new valve spring, it may be down on power. But you have to go in there and figure out, okay, it's not down on power probably for friction on the valve spring, it's down on power because the valve moves some way differently. So if it's a lighter spring, maybe the cam's it's not deflecting as much. It's acting bigger than it needs to be. So you may have to go in there, okay, if it's acting bigger, well, I can put that 4,000 slash in it and make it act 2 degrees smaller. That might get a little bit better. So you're always constantly trying to figure out, after I'm going to make one change at a time, I'm going to re-optimize.
Right.
If it gets way better, I'm going to doubt it.
Exactly.
If it gets a little worse, I'm going to re-optimize this and make sure that I learn something. When somebody just changes the lobe separation on a cam, if he goes from 115 to 113, he's changed all 4 events, he's changed the overlap, he's done a lot of different things. 2 of these things may have been worse, one of these things may have been the same, and one of these might have been better. He has no idea what he really did.
Yeah.
If you can change one valve event at a time, if you can change one part at a time, if you can change one tuning aspect, re-optimize and go back through it. And I think that's the biggest thing. Don't be a parts thrower. Realize that these are very much intricate systems. They're all working together, and really evaluate it most. The other thing is just really looking at these motors want to talk to you.
Yes.
They do
talk to you.
They do talk to you. If you talk to most of your guys who run NASCAR engine programs today, they started their career in teardown. The reason they started their career in teardown is their boss saw something that looked really good about them. They didn't stick them in teardown for punishment. They stuck them in teardown so they could see how these engines come off the racetrack and really look at them and lay them out and have all the interest stuff. like the guy at the shop saying, "Hey, look at this, Billy."
Right.
You know, Spinny be like, "Hey, look at this." You know, you get that type of setup. So look over your engine, look over the parts, watch what's going on, be a student of your engine.
All right, a couple more. We got just a couple of minutes remaining. John says, just to tie it all together, that I've learned more from Billy than just about anybody, or at least he helps me start thinking in another direction, and that is helpful. Great compliment right there. Yeah. And then Bob, who is a millennial, says, not that that matters, he wants to ask about, can you open the intake valve too fast on a 2-valve, ignoring dynamics? Is it possible to open it too fast?
You know, there might be a thing, because where does this piston get closest to the valve? And well, it's probably about 10 degrees after TDC. So if I make the valve opening really close and I can't hit this guy, I can't crack the valve till here. But if I open it a little slower and still can't do here, I can give more time for the exhaust system to talk to the intake by opening it a little bit slower. Most of the time we do our low shock lobes, it's for dynamics, not for power. But we totally believe there's something going on for power, especially around peak torque, where we can run the same compression ratio, the same piston to valve, and give just a little bit more time. Because when you open the exhaust valve, there's about 10 atmospheres of pressure still pushing on top of this piston. That creates this shock wave that goes down the header. When it hits a step or the collector, it's reflected back as a negative wave. So you have positive pressure going down, reflective is negative pressure coming back. You want that negative pressure to get back to the chamber right when you're starting to open the intake valve. So you get it past the exhaust valve into the chamber.
Yep.
If I can open that, if I can have that wave tuning correct and I open that intake valve a little bit sooner, then maybe I can create more momentum in the intake tract and better fill it, even with the slower opening, because I have this piston that is just totally believes the Heisenberg uncertainty principle and the whole space-time continuum deal, that I cannot have two objects occupying the same space at the same time.
And there you have it.
Yeah.
Excellent work, Billy. Thank you very
Thank
much.
you.
This has been great. Obviously, everybody loves this kind of stuff. Lake,
Fantastic.
right? Isn't it? Like,
Yeah.
I like listening to smart people talk.
And one thing,
really good.
for the people who are watching this, the one thing that I would advise anybody to do is what John talked about perspective. When I go to seminars, I'm not looking so much for answers as I'm looking at different ways to look at a problem. So if every time that somebody gives a presentation, when they're talking, when they're doing something, if you can try to take away one bit of perspective from each of the sessions, you don't know how much that'll improve your career, how much that'll improve your ability to do your job over time.
Amen, brother.
Yeah.
That's it.
Yeah.
There you go. Engine Performance Expo rolls on. This is exactly the kind of content you're going to get for the rest of the day.